is not totally reasonable if you're talking about just like a few atoms, because one iron atom weighs 9.27 times 10 to the minus 3 grams. So you can't just take out a scale and measure one iron atom. First of all, you won't see it. Second of all, there's no scale that goes to negative 23. Okay? So because things are so small, we come up with this new measurement, which we're calling the mole. Whoa. Don't write in highlighter. So MOLE is how you spell it. It's abbreviated MOL. The E was too much to write. Okay. I looked up why it's MOL because I just never, maybe I learned it a long time ago but forgot it. It comes from the German word. Is there anybody from Germany here? The German word for molecule, which is MOLUKI, or I forget how they spell it. But essentially, they just shortened it to MOL. Okay, so that's why we use MOL. So everything when you get an answer and I say how many moles of something are there, sometimes I'll just write 2.4 moles. Okay, you'll see that a lot. Sometimes I'll write E. MOL is the same as MOLE. It's up to you. When we do concentrations, you'll see things like 2.4 moles per liter. That's how it'll be written. Okay. So it's just the abbreviated form. Okay. So the mole, it's the fundamental thing that we use to measure the amount of things in chemistry. Okay. Amounts. All right. So I will say measure out 2.4 moles of something or half a mole of something. All right. So it gives us a unit that we can work with essentially. All right. So what is 1 mole? Now they've changed the definition. When I first went through school and stuff, the definition of 1 mole used to be number of atoms in 12.0 grams of carbon 12 specifically. So if you had 12 grams of carbon 12, that would be 1 mole, and the amount of atoms in there is what it was. They've changed that. They changed it in, I think it was 2019. To it's a slight subtle change, and I'm not going to ask you to reproduce this. Where is it? I looked it up this morning. Yeah, and of course I don't have it. All right, that's okay. They basically just change it to, well, I'll give you the number and then I'll say what they changed it to. The number is, well, it's that number there, big yellow thing there, but we're going to write it as 6.02 times 10 to the 23. All right. So the new definition, again, I'm not going to ask you the definition of what it is. I will ask you what is this number. It's called Avogadro's number. That guy right at the beginning that had the 17 names. This is Avogadro's number or constant. Come on. I never write number. I was always just put the number sign for number because I'm lazy. Okay. Avogadro's number. Or constant. It technically doesn't have units, but we'll look at it sort of does. They've just defined a mole as just this number. They've dropped this sort of definition of it's the number of atoms in 12 grams of carbon 12. All right, so now they would just say a mole is just 6.02 times 10 to the 23 particles or molecules or atoms. Okay. So a mole is like saying a pair or a couple. If I said there's a pair of apples, how many apples do you have? 2. It's a way to represent things. If I say you have a dozen, what's a baker's dozen?
13.
What's a gross? Sorry? What? Dozen is 12. A baker's. See, I was thinking baker's dozen as I was writing the answer of dozen. There you go. 12, 13. All right. Baker's dozen 13. What's a gross?
Is it 24?
Nope.
36?
You can't just guess numbers. It's a dozen dozens.
144.
So it's 144. I've never heard anybody use gross to represent a number before, but that's what it means. It has a meaning. It's a dozen dozens. We're not going to do that. Okay? And a century would be 100, right? Okay. What's a mole?
6.02 times 10 to the 23.
6.02 times 10 to the 23. All right. So it's the same idea. You can have a dozen donuts. You have 12 donuts. You could have a mole of donuts. If you had a mole of donuts, how many donuts do you have? 6.02 times 10 to the 23 donuts. That's a lot of donuts. Okay. So that's what this represents on the next page.
Isn't there like some field of study where it's like never mind.
Okay. All right. So just like anything, if I say you have a mole of anything, you have 6.02 times 10 to the 23 of that. So a mole of apples, 6.02 times 10 to the 23 apples. A mole of students, blah. A mole of carbon, which is something we will say, you have 6.02 atoms of carbon. Okay? Okay. The next part here is kind of the same thing. We're just going in reverse. We're not going to do that. If you say you have a mole, you have 6.02 times 10 to the 23 of whatever I say you have. Okay?
That number on there, I don't think you can see it because of the chairs, but that number, it says like the 6.02 and then a bunch of numbers, and there's different numbers. There's like different numbers. In the
after the 2?
Yeah, after the 214. On that one,
Is it really?
214, 179.
Over there it's 179. Up there it's
076. There's controversy, people.
Can we just like take?
We're just going to use 6.02 times 10 to the 23. I'm going to read that afterwards. I know when I was in university, there was something where they corrected it, and I forget, it was like down here somewhere. But they realized there was a mistake that they've been using for years. I mean, it doesn't really affect your calculations because, so there.
It's like all those zeros. Is it like actually approximately all those, or is it just rounded? Like, are those all zeros?
I want to say yes, but now I'm hesitant to say yes.
Like, you're telling me that there's not just like one extra one, like at the end?
No, but I just said I want to say yes, but now I'm hesitant to say yes. I will look it up to see if there's a specific number. Okay. Okay. How big is this number? Like, we see numbers, especially when you write it this way, 10 to the 23, and we understand, okay, that's big. But how big is it really? Okay. This number is massive. All right. So there's some analogies here to put it in perspective. And this first one, I didn't believe this first one, so I did the math, and this first one is true. If you had a mole of pennies, not dollars, pennies, okay? You would have enough money so that you could spend $1 million every hour, day and night, for the rest of your lives.
Everyone on Earth.
Yeah. Think about that.
That's a lot of money.
That's insane. Okay? If you had a mole of pennies, you could stack them and go back and forth to the sun 500 million times. Stacking the pennies. Like, we just did a lab with pennies, right? They're not very big. Just kind of boop, 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 boop. You go to the sun, back. A whole bunch of times. If you had unpopped kernels for popcorn, you could cover the U.S. 9 miles deep in popcorn kernels. It's huge. Okay? It's a massive number. This is the one I did. If you have a mole of dollars, I think this is crazy, and you spent $1 million every second, it would take you 19 billion years to spend all the money. And that's the one I did the math on. And I was like, because that can't be true. People are just making this stuff up. So I did the math, and I'm like, yep, that's true. 19 billion years to spend $1 million every second. That's crazy. You could cover, if you had sand, you could cover the U.S. in approximately 1 centimeter of sand deep. Okay. And yeah, if you had a mole of grapefruits, you would have the same volume as the Earth. All right. Basically, the number is real big. Okay. But when we're dealing with it, atoms are so, that sort of puts in perspective how big atoms are, right? And molecules, they're tiny, because we will work with like 2.4, 3.4, numbers that are bigger than 1 mole of molecules. Okay. So this is a insanely large number. All right. Avogadro and his number. He didn't really get any credit until he was dead after this, so poor Avogadro. But everybody says his name whenever they're in any science class, any chemistry class, I should say. All right. So here we go. Avogadro's number is the constant that works as a convenient conversion factor to convert between. Okay, so I said a mole doesn't have units. It sort of doesn't. The units change depending on what you're doing. Okay, so it's a conversion factor to convert between the number of particles. Now, when I say particles, particles can be atoms or molecules. Okay, of a substance, and an amount in moles. So, the conversion factor, we like our conversion factors in chemistry, is this. There are 6.02 times 10 to the 23 particles in 1 mole. Or you can flip it, just like we did with all our other conversion factors. 1 mole is 6.02 times 10 to the 23 particles. Remember, the particles are atoms or molecules, and you'll see it depends on what we're talking about. Okay. Let's do an example. Okay. Determine the number of molecules in 3.57 moles of CO2. So the only time, let's just do this. The reason this is molecules is because that's a molecule. It's multiple atoms stuck together. Okay. So we have 3.57 moles. Now, I'm going to say this, and I guarantee people won't do it, but you should do it. Okay, because they're going to start to get more complicated. We're going to do these are essentially unit conversions. Please. Okay, write out, I know you don't want to, write out mole and write out the actual molecule you're dealing with. Because when we get into chemical reactions, the molecules are going to change, all right, within the unit conversion. And if you don't write them out, you don't know what units you're canceling. Okay? So we have 3.57 moles of CO2. I'm trying to figure out number of molecules. So our conversion factors are here. What do I want in the bottom here? What unit? You want moles, right? Because you want the moles of CO2 to cancel. So that means I'm going to use this one, right? Because it has moles in the bottom. So we're going to say 1 mole. Now, this is where you have to do a bit of thinking. What are we dealing with? What molecule? CO2. There's only one in this case. So it's 1 mole of CO2 has 6.02 times 10 to the 23 molecules, because I remember I said up here, when we're talking about particles, it can be molecules or atoms, has 6.02 times 10 to the 23 molecules of CO2. Is that okay? All right. I'm focusing on these things right now. Okay. Moles of CO2 disappear. They cancel. You multiply this and this. What is the answer, people? How many sig figs should your answer have? 3 sig figs, right? What is the answer? I actually don't have it in front of me, so. Sorry? 2.15 times 10 to the 24. What? 2.15 times 10 to the 24 molecules of CO2. The units are going to start to matter now. You're right, it is particles, but I'm going to want specific things. So 3.57 moles has 2.15 times 10 to the 24 individual molecules of CO2. Okay. Determine the number of moles present in a sample of NO2 made up of 3.13 times 10 to the 24 molecules. So that's what we're given. We're given, I hand to you in your hand 3.13 times 10 to the 24 NO2 molecules. So 3.13 times 10 to the 24 molecules of NO2. I'm trying to convert this to moles. What units do I need down here? This. Whatever this is needs to be down here, right? Because I want that to cancel. So the only conversion factor we have right now are these two. Which one am I going to use? We use this one, right? Because 6.02 times 10 to the 23 particles. Particles, remember, means atoms or molecules. Okay? So we write 6.02 times 10 to the 23 molecules of CO2 is 1 mole. It's not CO2, of NO2. Is 1 mole of NO2. Where's my calculator?
Sharpen into pencil.
Is that what that is?
That's probably a pencil sharpener.
That is a very loud pencil sharpener. So if you divide those, you should get, how many sig figs in our answer?
3.
So I get 5.1993. What does that become? We have to have 3 sig figs in our answer. 5.20. What? Those cancel. Moles of NO2. Okay? All right. Determine the number of oxygen atoms in 3.57 moles of CO2. Okay. If you get a question like this, I'm looking for oxygen atoms. So we start with 3.57 moles of CO2. That's what they give us. I need to get rid of moles. What's our conversion factor for moles? Which one of these am I going to use? First or the second one? One on the left, one on the right. The left one, right? I want to use the left one. Is that the one I want to use? Are you sure? Yeah. Yeah. Because we're given moles. So I need moles to go away. So I want moles in the denominator. So I'm using this one. So I got, whoa, 6.02 molecules of CO2 are in 1 mole of CO2. Does that make sense to everybody? We're not done. Does that first step make sense? Because now what will happen is moles of CO2 cancels, and I'm left with molecules of CO2. Am I looking for molecules of CO2? What am I looking for?
Oxygen atoms.
Oxygen atoms. So then you ask yourself, how many oxygen atoms are there in CO2? 2. So that means 1 molecule, I don't need to write plural, molecule of CO2 has 2 oxygen atoms. Does everybody see that? Okay, this is going to start to become a common thing because they'll start to ask for a number of atoms in a molecule. All right. So then our molecules of CO2 cancel and we're left with oxygen atoms. What do you do with the top layer? You multiply them all together. So 3.57 times 6.02 times 2 should spit out your answer. And I get 4.29828 times 10 to the 24. How many sig figs should your answer have? Should have 3, right? Why should have 3 and not 1?
Because 2 oxygen atoms or 1 molecule CO2 or 1 molecule CO2 is a conversion factor, which means it has an infinite number of sig figs.
Yeah, this has an infinite number. It's a fact. It's not a measurement, right? Because you just look at it, there is 2 in every molecule. So this you ignore. It's these ones, and it's usually this one. It's going to determine everything. Okay? So we should have 3 sig figs, which means I take the first 3, then you look at the one beside it. What does the 8 do? Kicks it up. So what's the answer? 30 times 10 to the 24. Oxygen atoms. Okay? Is that all right? I know this might seem straightforward, but this is the beginning. If you can't do this stuff, you're going to struggle for the rest of the unit. Actually, you're going to probably struggle for the rest of the course because this is going to set us up for a lot of stuff we do from now on. All right? Your conversion factors, I'll give those to you, but we're going to use them so often you'll probably just know them. It's whether you want your particles in the top or the bottom. It depends on what units you're canceling. And then if they're asking for specific atoms in a molecule, just remember this last one here. All you do is you look at the molecule and you just look at how many of each atom there are. Okay? I would like you to do the next page, please. This stuff, 5.1. And then I'm going to enter your test scores and then hand them back to you. Or, okay.
Oh,
So, molar mass. It has the word mole in it. So what do you think the molar mass is? If I say the word mass, what units are we talking about? Grams, right? The mass of something is measured in grams or kilograms. Ours is going to be in grams for the most part. The molar mass.
moles per gram.
Grams per mole, moles per gram, essentially, yeah. It's the mass of 1 mole. Okay? So the molar mass is the mass of 1 mole of a substance. Their units are grams per mole. Okay? And nobody likes writing out molar mass. Chemists are lazy, so we write mm. Mm means molar mass. Okay? Part of doing chemistry is learning the whole language around it. All right? Okay. The molar mass of an element, so as soon as you see the word element, we're talking about the periodic table, is the same number as its atomic mass. Okay? So if you have your periodic table, carbon, it'll say 12.011. That is the atomic mass. That means that 1 mole of carbon atoms weighs 12.011 grams. Or if you have 12.011 grams of carbon, you have 6.02 times 10 to the 23 carbon atoms. Okay, because it's 1 mole. That's the molar mass. All right. So you got your periodic table, or I'll pull mine up here. So we're going to do the molar mass of iron, calcium, and tellurium. Where is my periodic table? 11 data booklet. There we go. What's the molar mass of iron? Fe. Oh my gosh. Whoa. Boom. 55.8. What are the units? Grams per mole. So that means iron is 55.8 grams per mole. What's calcium? 40.1 right here. Boom. This number is the molar mass of the elements. Okay? And the final one? Nice. 127.6 grams per mole. Okay. Now, what if you stick a bunch of atoms together? You get a molecule or a compound. Okay? So now we can use the molar masses from the periodic table to determine the molar masses of compounds. So, HCl, this is almost, whenever you're doing solution calculations and stuff, this is almost your first step every time. So the molar mass, as soon as you see molar mass, you're going to your periodic table of HCl. What is HCl? Starts with hydrochloric acid. It starts with a hydrogen, so you know it's an acid. If it's in aqueous, it's hydrochloric acid. If it's in gas phase, it's hydrogen chloride, right? They're both right. You're both right. Okay? So, what is hydrogen? What's the molar mass of hydrogen? Hydrogen has a molar mass of 1 gram per mole. What does chlorine have a molar mass of? 35.5 grams per mole. So what's the molar mass of hydrogen chloride? Is the atom together. 36.5 grams per mole. Is that the right number of sig figs? Yes, it is, right? Because when you're adding or subtracting, you're just looking at the decimal places. Okay? All right. We'll just do these and then we're done. Oxygen gas. Be careful. What's the formula for oxygen gas? It's O2. It's a Brinkelhoff, right? Oxygen gas is O2. So, what's the molar mass of oxygen? 16.0? Yeah. So if you look on your periodic table, oxygen, right there, has a molar mass of 16. How many oxygen atoms are there? There's 2. So it's 2 times 16.0, which is 32 grams per mole. So if you had 1 mole of oxygen atoms, it would weigh 32 grams. Okay? All right. Magnesium nitrate. Can anybody? So the first thing, this is why we did naming. You got to figure out the formula. What is the formula for magnesium nitrate? So what's the symbol for magnesium? Mg. What's the charge on magnesium? It's +2. What is the formula for nitrate? It'll be in your polyatomic page, in your data booklet. NO3. What's the charge? -1. So what's the formula for magnesium nitrate? Mg NO3 2. Right? Does everybody agree with that? This is important. Okay. Now, I want to know the molar mass of this. So the first thing we got to do is we're going to do magnesium. How many atoms of magnesium are there in magnesium nitrate? 1. What's the molar mass of magnesium? Look on your periodic table. 24.3. There's only one of them, so I can just leave it as 24.3. Okay? I don't know why I drew a line there. All right. Nitrogen. How many atoms of nitrogen are in MgNO3? 2, right? Because this 2 goes to that. So you have 2 nitrogen atoms. What's the molar mass of nitrogen? 14.0. What's 2 times 14? 28. So these should all be in. How many oxygens? 6. So O, I've got 6 of them. What does oxygen weigh? 6 times 16.0 is 96.0. Now what do I do to get the answer? You add them all together. And you get 148.3 grams per mole. So the molar mass of magnesium nitrate is 148.3 grams per mole. Okay? We're going to stop there. We'll pick this up tomorrow. This is the beginning of